Hello everybody, and welcome to the top of page 32. In this video, we'll be bringing together some general facts about finite dimensional vector spaces in the specific situation in which we know what the dimension of the vector space is. Turns out that knowing what the dimension of a vector space is, that's a very useful piece of information. We can make a lot of conclusions about that. So let's maybe start by reminding ourselves what it means to say that the dimension of a vector space is n. That's just telling us the number of vectors that has to be in a basis. Okay, so V has n vectors in its basis. We'll keep that in mind as we're going through this. And what we're going to do is to fill in four facts that you see over here, DF1 through DF4. The DF stands for dimension fact 1 through dimension fact 4. Okay, and we're going to content ourselves with just filling these facts in, maybe saying a few brief words about why it might make some conceptual sense. If this were a more advanced course, we'd probably go a little deeper and prove these things too. Okay, let's start with DF1 here. Okay, and if we read the first sentence, it says that every generating set for V can be reduced to a basis for V by deleting vectors if necessary. Okay, if you think about it, that kind of makes sense because we already know that a generating set for V is a set that's big enough so that we can build every vector that we want to in V. So there's a possibility that maybe that set is too big, and if it's too big, this is just telling us that we can reduce it to a basis by deleting vectors if necessary. What that means then is that every generating set of V has to contain at least n vectors. Okay, there's that number n, okay, the dimension of our vector space. Okay, so it's telling us that any generating set has to have at least n things in it. Okay, and we can make a similar statement about linear independence. DF2 says that every linearly independent subset of V can be extended to a basis by adding vectors if necessary. If you think about it, this kind of makes sense too, because a linearly independent set is one that's small enough so that there's no dependencies among our vectors. So maybe it's too small to build every vector in our space, and in that situation we may need to add vectors to get up to a basis. Okay, so said another way, that means that every linearly independent subset of V contains at most n vectors. Okay, can't be bigger than having n vectors in it. Okay, and then we move on to Df3 and Df4. Okay, so Df3 says a generating set for V that happens to contain exactly n vectors is actually a basis for V. Okay, let's think a minute about what this statement is really saying. Okay, so first of all, the n, I'll keep reminding you of this, the n is the dimension up here. Okay, and we might remember that the definition of a basis, it's a set that has two properties. It's got to be linearly independent and it has to span. It's got to be a generating set. Okay, well, what DF3 says is that if we only have one of those properties, we know that it's a generating set, but it happens to contain the right number of vectors, this magic number n, then it's a basis. It has the other property automatically. It's also linearly independent. Okay, and then DF4 is similar. It says that if we start with just the property that our set is linearly independent and it also has exactly n vectors, that's enough to say that it's a basis. Okay? So there's the list of four very important properties. We're going to find these properties to be very useful in some of the problems that we do in upcoming videos.